All right, guys. Today we're going to be looking at a new pattern, and this video will be the introduction for the pattern, and I'm calling the pattern the DFS pattern. So let me kind of add in a title here. Say DFS pattern. Now, in terms of the number, this is the second pattern that we are looking at after binary search pattern, and so in this pattern, we're going to first look at the basis that's allowing us to implement a DFS pattern, and then we're going to look at the DFS algorithm itself, which is short for depth first search, and then we're going to look at the most important questions that you need to cover in order for you to solve any backtracking, depth first search, graph based or tree based questions with confidence in JavaScript. So let's get started here. So before we get into what DFS is and how it started initially, let's go a little bit deep into the theory of recursion and what it means in computer science. In plain language, recursion would mean a function calling itself. So it's a way of saying that I want to accomplish a task by repeatedly calling the same piece of code again and again. So in real life, let's assume that there are 6 friends who want to go to a dinner, right? So let me give you a real life example, right? So there are 6 friends. Let's call them friend A, friend B, friend C, friend D, friend E. Actually, let's keep it 5. It'll be easier for us to discuss it. A, B, C, D, E. And now it's very important here for all of them to go for a dinner night, right? Dinner night. And A kind of initiates the plan. A says, okay, start planning for the dinner. So what A does is A calls B. A says, okay, let me call B and see if he is interested in joining me for this dinner night, right? So A calls B, and then B says, I am willing to come, right? I am willing to come, but let me call C to see if he is willing to join, right? And B calls C, and C says, I am willing to come as well. I'm willing to join as well. Let me ask D if now she is willing to come, right? Willing to join, all right? And so C calls D. D says, okay, I'm good, but hold on a second. B on the call. Let me call C. Let me call E. And get back to you. And now one thing to note here is everyone's waiting on the call, and everyone's saying, let me get back to you. And so D eventually calls E, and E says, I'm good, right? So E is coming. So what ends up happening here is E says, I'm good. Now D has gotten an answer. So D replies back to C saying, okay, I'm willing to join for the dinner night as well. C says, oh, that's great. Let me inform B, who's still on the call. So C says, oh, we are all good. So B did not have to call D and E separately. C did the work for B, right? And so B finally says, returns the response to A saying, everyone's good, all of us are joining, we'll have a blast. All right. And so this is a real life example of recursion. All of them were waiting on the line, on the call, until the last person said yes, and they all started informing each other in the reverse order. And that is how recursion works, right? And this is a real life example. Now imagine we have a function and it spawns new instances of itself and labels them different names, right? Labels them with different names. And so a very simple example here, very simple example that we can take is of factorial, or even let's try to convert this real life example into code, right? Let's say def dinner plan, or my bad, in Python it's def, but in JavaScript let's do function dinner plan, and then we have person, right? Now a person is going to say, okay, so the first thing that we need to say is return call or dinner plan, that's a function name, and then say next person, right? So let's assume that this was the first call made by A. So A calls dinner plan and say starts dinner plan, right? And A calls the dinner plan, and by passing in B, right? By passing in B. And B says, okay, let me call the next person, which is C, right? And C says, let me call the next person E. E says, let me call the next. C says, let me call the next person, which is D. D says, the next person's E. Let me get back to you after that. And eventually, if the next person, or in this case, if the person is equal to E, then we know, return true, right? Then we know for sure that E is coming, and so the current person relied on E, and so he eventually says, okay, return true, because E is willing to join us for the dinner call, for the dinner plan, right? And so on and so forth, until we get to the very last call, which is A. A gets his answer, then everyone's planned a dinner in a very efficient way, I believe. And so this is a very simple example of recursion. A is an external caller. A calls the dinner plan from outside of this function, and then passing in B as a person, but B, being the entity of the function, calls the function again and again and again, again once basically, and then the persons down the line call the function again and again and again until they get to E and get a response from E, which is true, right? And then all the other persons who are waiting on call are going to get a response true, and at the end the external caller A is going to get true as a result. And so this is a basic example of recursion. And now that we have an understanding of how recursion works, we need to understand how it's done, like how the computer actually understands recursion and processes it, right? So the computer keeps track of the calls using a call stack behind the scenes. And so we have a call stack where each of these calls that we are making are stored in order, but then the last in first out property is still maintained. So E was the last to get into the call stack, and so E is the first to be popped out. And then D was the second last, so D is the second last, second first to get popped out, and so on and so forth. And so there's one more thing that we need to understand here, that the current function call is always paused or put on hold until the next call reverts back with a response. And so this is the third point here. And so this is how computer understands recursion. The implementation will require an exit condition, will require a function call within that function, and then will eventually require a return statement. Without these three things, it's almost impossible to implement recursion. So whenever we are trying to write a recursive function, we first need to decide on the exit condition or the base case, which would be the very first code block within your function. And then you need to know the function call, where you want to call your function. In this case, we are calling the function right here at the very end. And then you also need a return statement. In this case, the return statement happens to be the function call itself. So we're just going to return a dinner plan. But you can have different calls here. You can have function calls as you see fit. but these are the three crucial pillars of recursion implementation, without which it'll be almost impossible to write a recursive function. And so now that we know a little bit about recursion, let's go into a bit more detail about what DFS is, right? DFS is nothing but depth first search, right? Depth first search. And then the concept is pretty simple. It's about going through a binary tree or a graph data structure, right? And in simple terms, if we want to explain DFS, it's like utilizing recursion to get to the very last decision and then backtracking until we get to the very first decision. And so a simple example of DFS in this case would be to consider a tree, right? We could call it a binary tree in this case, and that tree needs to be parsed, and we need to find a target from the tree nodes. And so let's say we want to write a function. Let's call it DFS, very simple. We have the root of the tree as the reference, which is the starting of the tree. Now root is giving us access to the very first node in the tree, and then roots left, roots right are going to give us the nodes further down the line. So we have the starting of the tree, we have the target that we need to look for in the tree, and so you can assume that a node, right, a node is going to be like hold a pointer which represents that node location, and then it's going to have a value which would be an integer, right? Value would be integer, pointer will be the reference to this node, right? Let's assume this is our node structure here, and then every node has a pointer, and it's usually referred by its pointer. So root is just a pointer. Root.val will give you the value that's within the node, right? And so it's going to be an integer value, and the target again is an integer value that we are looking for in the binary tree. And so the first thing that we do here is check, right? If root is something that does not exist, if not root, then we're just going to return null. Well, that's logical. And then what are the other possibilities? So if root's not null, we're going to end up not hitting this condition, so we need something else here, right? We say root.val equal to the target, because we are looking for the target, right? And if it is equal to target, then we have found our root, and we can end our recursive calls right here. Now, if it's not equal to target, then we need to look further down the line, right? We say look further down the line. And so in order to look further down the line, you would have to say, okay, let left equals DFS, call your function, passing the left node of the tree, left node of your current node, and that's about it, right? And if you say left is not, now once you have done that call, you assume that you have gotten your result, and then say if left not equal to null, return left, right? And then if you do this for the left node condition, we do the same thing for the right. We say okay, let right equals DFS root.right, pass in the right node of the current node, and then you don't have to check for anything because you already have an initial condition checking for the root, checking for the incoming node whether it's null or not. So you just return right. Okay, so look further down the line, look for the look in the left subtree for every node, and look in the right subtree, right? And this is how the vanilla DFS looks like, assuming that every incoming node, we can call it incoming node if you want to. So we can kind of say incoming node, right? So every incoming node in the DFS function is either going to have one child node, two at max child nodes, or no child nodes at all. So every time we're saying, okay, look towards the left first and keep going to the left until we find something. If we don't find anything, come back and then start looking at the right nodes. And so if, let's assume that you found your target in the left one, these lines here will never be executed. You will end up returning the incoming node as your target node when your function hits this condition. But if you don't find your target value in the left subtree, then you eventually have to get to the right subtree of the root node. And if you find the target in the right subtree, you end up returning right here. Only then these lines will be executed. Now, if the root node, which is the very first node, which is passed by the external caller of this function, for example, external caller could be anywhere outside the function. So say DFS passing the root node of the tree that I have, and then the target is 3, right? Look for 3. And then this root node has been initialized somewhere else. The tree definition is somewhere else. We are here only concerned about finding the target in the tree when we are given the tree's root node's reference. And so incoming node gets here and say if the incoming node is not null, and if the root node is itself the target node, then we just return the root node. None of the lines will ever execute, right? And so this is how DFS works. And backtracking is a fancy word that was given to the method of going in depth and then tracing back the results to the very original point. And DFS is kind of the implementation part, and backtracking is just the name given to the way we think about problems, which involve, well, call stacks and recursion. And so in simple terms, the action of retracing steps is called backtracking. Right? Backtracking is nothing but the action of retracing the previous steps, and DFS is actually the implementation of backtracking, where we go to the very end and start tracing our results back to the original point. And now that we have DFS and backtracking and a little bit of understanding about recursion, we can go ahead and install simple basic questions, and then we're going to move to more advanced ones in the upcoming videos. So before we leave for today, let's try to understand what the time complexity and space complexity is going to be. Space complexity is always going to be big O of n, because there's a call stack involved. Well, the call stack is behind the scenes. You're not initializing a new data structure to store the calls. However, there is some memory being used when the process, or in this case, the node process that you're going to run it on, is going to use some amount of memory to store the call stack. And so n would be the number of calls, right? And then the time complexity here is going to be a big O of, again, if there are n nodes, you're going to visit all the nodes in this binary in this binary tree, sorry. And so you'll have big O of n again, where n is the number of nodes in the tree, right? And this was the basic DFS. I would say we can memorize this template and reuse it wherever we want to. And the very simple understanding is, first check if the incoming node is not null. If it's not null, move forward. Check if it is target. If it's not target, exhaust all the nodes in the left subtree. Well, if you still don't find an answer, go to the right subtree and exhaust all those nodes as well. and then eventually return right. So this is a very simple example. I'll see you in the next video with a new question, and that question will introduce concepts like DFS implementation and modified backtracking. Thank you so much, guys. See you in the next one. Bye bye.